Pluto is a distant and dim, relatively small astronomical object that was once considered part of our solar system. However, recent and surprising announcements by leading space experts Neil deGrasse Tyson and Mayoku have brought Pluto back into the spotlight. They suggested that this remote body could potentially be on a likely crash course with Neptune. They aren't merely hypothesizing, they're issuing a warning. This miniature world may be heading straight for a catastrophic encounter with Neptune. But how could such a thing be possible? And what would the aftermath be if an enormous impact like that truly took place? Are we seeing an odd cosmic illusion, or is something far more tangible, and much more alarming, speeding toward us? Pluto's path comes dangerously close to Neptune's. Neil deGrasse Tyson and Mayoku are raising the alarm. If there's even a slight adjustment, we could be facing a planet-wide catastrophe. Might Earth be at risk as well? More crucially, how could such a cosmic occurrence even come to pass? Join us as we delve into the possible consequences of a Pluto-Neptune collision. Pluto, once officially a planet but later downgraded to a dwarf planet, remains a source of intrigue in the vast universe. As demonstrated by current models from leading researchers, Pluto's path passes dangerously close to Neptune's. Well-known astronomers Neil deGrasse Tyson and Mayoku are both alerting the world to a potentially dangerous interaction between these two entities, which could imply a substantial hazard for Earth. Yet how could this scenario unfold? Pluto's journey around the Sun is unlike any other orbiting body in our solar system. It takes an incredible 248 Earth years to complete one revolution. Since its discovery in 1930, it hasn't even made one full orbit. Still, the intrigue doesn't stop there. Pluto's orbital path is highly stretched out, much more so than the generally circular paths of the main planets. Even more fascinating is its orbital inclination, a tilt of 17 degrees compared to the Sun's plane. This trajectory is far more irregular than those of the other planets, adding layers of complication to Pluto's movement. Arguably, one of the most fascinating aspects of Pluto's route is that it intersects Neptune's orbit for about 20 years in each orbital cycle. Pluto is actually closer to the Sun than Neptune, defying what we'd expect based on their standard positions. This raises the usual question, why haven't they collided? The answer lies in the gravitational effects of nearby celestial giants. Studies into the path of Pluto began shortly after it was found. Early astronomers attempted to make sense of its odd orbit. While most planets move in loops that are in line with the plane of the Sun, Pluto's path is slanted and uneven. The puzzle grew deeper when scientists realized Pluto's orbit crosses that of Neptune. The stability of Pluto's motion, despite these strange features, proves the subtle intricacies of space mechanics. The three-body problem, understanding how three celestial objects like Pluto, Neptune, and the Sun influence one another through gravity, is central here. It's like predicting future positions based on their initial placements and mutual gravitational pulls. In Pluto's case, this complexity reveals how its movement, Neptune's orbit, and the Sun's pull all work in an interlinked system. Terms like asynchronous oscillation, orbital drift, and the VZK wobble are key to decoding this riddle, as highlighted by astrophysics experts. What helps maintain celestial bodies traveling in a stable direction is asynchronous oscillation. In Pluto and Neptune's case, this means that when Pluto moves through Neptune's path, it is placed at least 90 degrees away from Neptune, a safe angular buffer that prevents a crash. Orbital drift, on the other hand, involves the vertical displacement of a body as it circles. For Pluto, this suggests that when it draws near Neptune or another large planet, it is much higher than their orbital paths, adding another safeguard against potential impacts. Another important factor is the VZK wobble, named after researchers Zell, Kai, and Koku, who studied the gravitational interactions of space objects. It describes how three massive entities, like Pluto, Neptune, and the Sun, exert forces on one another, influencing their movements. In Pluto's situation, the VZK wobble offers insight into why its orbit near the Sun appears erratic. Even though its path may seem unstable, this wobble helps keep it smoothly orbiting over very long periods. The VZK wobble shows that while space may seem chaotic and unpredictable, underlying principles still maintain a degree of stability. These forces support Pluto's consistent motion, preventing a Neptune collision or wild deviation. This three-body dynamic is vital to understanding how orbits shift due to gravitational interference. Studying it gives us more clarity about Pluto, our planetary group, and even distant galaxies. Computational models from the 1980s indicated that while Pluto's orbit is stabilized by certain features, it still exhibits unpredictability. Minor changes in starting conditions can cause major deviations over centuries. Still, Pluto's orbit has remained steady over remarkably long durations. Modern automated data has allowed us to better observe how the massive planets Neptune, Jupiter, and Saturn influence Pluto's journey around the Sun. Pluto and Neptune share a special orbital rhythm. For every 2 laps Pluto makes, Neptune completes 3. This synchronicity helps preserve Pluto's route. But Neptune isn't the only player. Jupiter's powerful gravity plays a major role in keeping Pluto's path stable. Saturn also contributes. Studies show that Jupiter's mass is sufficient to help maintain Pluto's trajectory for possibly billions of years. It appears that Neptune, Jupiter, and Saturn are collectively working to ensure Pluto travels safely through space, avoiding danger. These unusual but vital systems are crucial to keeping our solar system balanced. Space would be vastly more chaotic without them. Objects like Pluto might crash into others or be expelled from the system, creating chain reactions across the cosmos. Particularly in Pluto's case, and concerns about future encounters with Neptune, understanding its movement is essential. This gives us a clearer view of the ever-changing, dynamic nature of our planetary family. Pluto's case shows how even seemingly unstable orbits can achieve harmony through complex gravitational and kinetic balances. It also highlights the need for constant observation and analysis of these anomalies to better understand our place in the universe. Exploring the outer realms of space often brings us face to face with the strange nature of celestial phenomena. Pluto's orbit is a perfect representation of such irregularity. The concept of orbital chaos, which refers to how orbits are highly sensitive to their starting conditions, is clearly at play here. This indicates that even minor adjustments to Pluto, whether in its speed or position, can dramatically alter its long-term path. Using computer simulations has greatly aided scientists in examining Pluto's behavior. These tools use complex formulas to replicate how Pluto and planets like Neptune interact through gravity. By tweaking initial variables, researchers can observe how even minor adjustments may completely change the outcome. Such simulations show just how fragile orbital relationships can be over astronomical timescales. Though current models indicate that Pluto is in a stable resonance with Neptune, meaning they never get close enough to collide, there's still a growing concern among some researchers. What if an external force, such as a passing object or a slight gravitational nudge from another celestial body, alters this delicate balance? Could it tip Pluto onto a collision course? Astrophysicist Mayoku warns that while such a scenario is unlikely in the near future, it's not impossible. Our understanding of space is constantly evolving, and so too are the technologies that allow us to study it. As these systems grow more precise, we might uncover previously unseen instabilities or interactions that reshape how we perceive planetary motion. The hypothetical collision of Pluto and Neptune would be nothing short of catastrophic. It would unleash massive energy, potentially altering the orbits of other planets and scattering debris throughout the solar system. If any of that debris reached Earth, the results could be devastating. Even if a direct collision never occurs, the gravitational shockwaves from a near miss might have far-reaching effects. This is why Tyson and Mayoku are sounding the alarm, not to cause panic, but to encourage vigilance and continued research. Our solar system is a complex web of interactions, and even the smallest imbalance can ripple outward in unexpected ways. Pluto, once dismissed as a cold and distant outlier, might hold the key to unlocking deeper truths about cosmic stability and chaos. In the end, Pluto's story is not just about planetary classification or orbital dynamics, it's about the fragility and wonder of the universe. It serves as a reminder that even the smallest celestial body can have a massive impact, and that watching the skies is not just a scientific duty, but a safeguard for our future. Pluto's destination, a cosmic puzzle. Back in the 1980s, shocking new digital models were revealed. Despite the fact that Pluto's orbit incorporates stabilizing factors like asynchronous oscillation and orbital resonance, Pluto's journey can still act as a drift. Unpredictably, a slight difference in its starting point or speed could produce vastly different outcomes in just a few years. Nevertheless, Pluto's path has held steady over billions of years, which suggests that beneath its erratic appearance lies a hidden consistency. Predicting the motion of celestial objects, especially those with erratic orbits like Pluto's, remains an enormous obstacle. The inherent instability of such systems makes long-term predictions full of uncertainty. While mathematical models are excellent tools for understanding and predicting space dynamics, they also reveal our limitations. These calculations rely heavily on accurate starting values, and even a small error can lead to drastically different results, making precision very difficult. Beyond the unpredictable nature of orbital paths, Pluto also symbolizes the continuous transformation and movement within the cosmos. Despite humanity's considerable achievements in astronomy, Pluto's unusual behavior reminds us how much we've yet to learn. Studying how massive planets shape Pluto's movement helps us better comprehend the dynamics of the solar system. It shows that each planet's mass and location can significantly influence others. So why are high-profile astrophysicists suddenly worried about a potential Pluto-Neptune impact, despite every cosmic mechanism intended to avoid it? Neil deGrasse Tyson, a renowned scientist and influential figure in public astronomy, offers a unique take on our planet's puzzles, particularly Pluto's unusual story. Tyson, known for advocating Pluto's reclassification as a dwarf planet, provides insightful commentary on how our understanding of orbits and the solar system evolves over time. He doesn't see the change in Pluto's status as disrespectful, but rather as a necessary correction based on growing scientific knowledge. Tyson believes that learning and adaptation are central to grasping complex orbits. He sees paths like Pluto's as a sign of how much more there is to discover. The wonder behind such mysteries keeps astronomy exciting. Yet, while Tyson is generally optimistic, his perspective on a possible Pluto-Neptune collision is far more sobering. His concern about Pluto's fate stems from his awareness of orbital instability. He acknowledges that Pluto has stayed safe so far, but even tiny changes accumulating over time could lead to disaster. Pluto's orbit, especially its overlapping section with Neptune, forms a fragile cosmic rhythm that may not last forever. Tyson argues that even minor shifts in Pluto's movement could lead to major consequences over thousands or millions of years. Such disturbances could cause chaos, or even a direct collision. Though this is not an immediate threat, it's a possibility unfolding on a time scale far beyond human civilization. Still, the cautious demeanor of Tyson emphasizes the importance of maintaining constant vigilance and further study of Pluto's orbit. Tyson isn't alone. Michio Kaku, a world-renowned theoretical physicist, also sees the possible mayhem that might result from planetary interactions. Like Tyson, Kaku is amazed by the universe's vastness, but he also understands the fragile balance of planetary systems and the unpredictable outcomes that may arise. Tyson and Kaku both emphasize the importance of relentless exploration into the invisible forces guiding orbital paths and the long-term future of our solar family. In conclusion, Pluto's circumstances reflect how our knowledge of the universe is in constant motion. Each discovery opens new questions. As astronomy advances, the slight chance of a Pluto-Neptune impact serves as a humbling reminder. The universe is full of surprises, and even seemingly peaceful planetary paths can shift drastically over time. Pluto's lessons inspire us to keep looking up, and to keep wondering what secrets the stars have yet to reveal. This sense of cosmic uncertainty doesn't just apply to Pluto. Across the solar system and beyond, celestial bodies interact in complex, often invisible ways. Moons tug on planets, asteroids shift subtly under gravitational influence, and stars themselves drift in response to galactic forces we're only beginning to understand. Pluto, distant and often overlooked, stands as a powerful reminder that no object in space exists in isolation. Its orbit is not just a line on a chart, it's a dynamic story written by gravitational dances with Neptune, Uranus, and perhaps other as-yet undiscovered influences. These orbital relationships form what scientists call resonant chains, where the movement of one body helps stabilize or destabilize another. If one link in that chain were to shift, say, due to an unexpected asteroid flyby or long-term perturbations from passing stars, it could trigger a domino effect with consequences far beyond what we currently predict. The stakes of such changes might seem abstract, unfolding over millions of years. Yet they underscore a broader truth about astronomy: our universe is alive with motion. And motion, no matter how slow or distant, has meaning. This is why researchers continue to model Pluto's orbit with increasing precision, using powerful simulations that take into account not only gravitational physics but also chaos theory and quantum-level uncertainties. The goal isn't to dramatize a potential collision with Neptune, but to understand the boundaries of what is knowable. In the process, we deepen our grasp of the cosmos and our place within it. Pluto may be small and cold, spinning in the shadowy outer reaches of our solar system, but its story is vast. It reflects the very essence of science: curiosity, complexity, and the ever-present possibility of the unexpected. And perhaps that's Pluto's greatest gift, not just the data it provides or the theories it challenges, but the enduring mystery it represents.